All right. Good evening. Thank you for coming, and thank you, Hendrik, for the talk. And actually, I will talk a lot about not writing code, so it's super cool. So before we can make sense of that meaningless title, let's try to begin with a small question. Is everybody in there a functional programmer? Yes? No? Yes? Oh, cool. So, what is functional programming good for? I mean, we are doing it for some reason, right? And what it is good at, actually. It's really good for modeling data. We have algebraic data types, we have pattern matching, we have type classes that helps us work well with ADTs. And we have immutability, we have many cool things. We have refinement types in Scala if you want. We can go very crazy with the typing. And yeah, functional programming is excellent for modeling complex data models. It is also pretty good at modeling effects. It has been all the rage the past few months about I/O monads and ZO and streams and functional streams and so on. So we are very well equipped to make sure that our business logic is separated from every mundane plumbing details of running the business logic. And in the end, the programs we build with functional programming look like pretty little boxes. Inside the box, everything is supposed to be pure. We have no side effect. We have immutability. We have very nice code that we can reason about and make it very testable, and we are very confident. And we try to push everything that's impure to the side, the effects and so on. Maybe that's why we call them side effects. I don't know. And we are very happy. We have our tiny little nice boxes and everything is good. But the problem is, these boxes, if we keep them closed, they are completely useless. We have to put data inside the boxes and get data outside the boxes. So the data, the thing that makes our applications worthwhile, have to go in and out. And so in every project, everybody has to write some code for serializing data in JSON, or maybe Avro, or protocol buffers, or I don't know, Thrift, or probably 3 other flavors of JSON, because why not? But also for validating user input, or reading configuration files, accessing data in database, generating random data for our property-based tests, pretty printing, and so on and so forth. That's a lot of code we have to write for every single project. And this code we write, it's very mechanical. It brings absolutely no business value, and it's overall very repetitive. And that's a problem because our job is to bring business value. It's not to write a JSON parser, right? So there should be a way to abstract all that away. So can we do better? The first idea, especially when you're a Scala developer, is to say, oh, let's use shapeless and derive all that boilerplate at compile time. Let the very powerful Scala compiler work for us. And we have many solutions for that. We have shapeless, I already told that. We have Magnolia that takes the same approach but is much faster at compile time. We have SchemaZ deriving. And also we have specific solutions. For example, if you are using Play, there is Play JSON that gives you, using Scala macros, formats for your case classes and ADTs. And we also have many specialized libraries like Scodex and Cersei and Avro4S and etc. But we end up with many different APIs that are difficult to customize, that sometimes, most often than never, slow down compilation, and especially if you use shapeless, are very, very unfriendly error messages. But it is not the main problem with compile time derivation, especially for everything that relates to serialization. Because if you derive at compile time your JSON codecs, for example, you are binding your code with the data that goes on the wire. And it leads to what I call the evolution problem. So imagine we have a very, very small system, microservice system with 2 nodes, only 2 nodes. And these nodes, they exchange messages in JSON. So for example, we have a message that has a field called name. And these 2 nodes, they talk to each other and they are happy and everything is good. And now we build a version 2 of our application and we start to deploy it. And of course, we don't shut down every node at once, update the version and restart the nodes. We do that on a node-by-node basis. So we deployed the version 2 on node 0. And this version 2 brings a breaking change on the format, because the field that was called name is now called username. So what happens once we have deployed version 2 on node 0? The node 0 receives a message from the node 1 that still runs the old version with a field called name. And so the node 0 doesn't understand the message anymore. It's a backward compatibility problem. And of course, the other way around, if the node 0 sends a version 2 message to the node 1 with a field first name, yes, that's it. The node 1 doesn't understand this because it doesn't know about this field, first name. That's a forward compatibility problem. The node 1 is not forward compatible with version 2. So that's the evolution problem. Has somebody already run into this kind of problem? Oh, okay, cool. So yeah, it's very sad. So let's try to solve that. And we'll see at the end if we can get our code deleting goodies as well. So to solve this problem, of course, we don't want to carry along the old versions of our ADTs in the code base. That's a no-go. And we also don't want to write every serializer and deserializer by hand. That's a no-go too. So to solve this problem, we need a way to abstract over the structure of the data and use this abstraction to, at runtime, derive serializers and deserializers, and that's it. And this kind of abstraction, it already exists, it's called a schema. So from now on, I will talk about a imaginary library that defines schemas, and I will present you how it works. It's based on a very, very simple idea. Our business objects are defined using ADTs. And ADT stands for algebraic data type. And in fact, all these types are produced by a very, very simple algebra. It can be reduced to three elements. The unit type, that is the type that has only one value, unit. A binary sum, that is, for example, the scalar either. And a binary product, that can be, for example, scalar tuple 2. And I will try to convince you that I can express any possible type with only these three elements. So for example, if I were to define a bit, which is either 0 or 1, I could say a bit, it's simply either unit. And to convince you that it can work, and that there is an isomorphism between bit and either unit, let's do a little bit of counting. Unit has only one inhabitant, its unit. Either AB has as much inhabitants as the number of inhabitants of A plus the number of inhabitants of B. That's why it's called a sum. So either unit has 1 plus 1 equals 2 inhabitants. That's exactly the same as bit, 0, 1. So there is an isomorphism between the two. Actually, there are multiple isomorphisms, because you can put the 0 on the left or on the right. Doesn't matter. The same goes with the product. A product of A and B has as much inhabitants as the product of the number of inhabitants of A and B. So if I want to define in the same way a byte that is 8 bits, I just define this product, nested product, and what I get is 2 times 2 equals 4, times 2 equals 8, blah, 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 to 256 inhabitants. Everybody is with me? Okay, cool. And I can go on forever, like options, for example. Option is isomorphic to either unit and A, option of A. It gets a little bit more complicated when I get into recursive types, because the Scala syntax doesn't allow me, for example, for list, to say directly a list of A is either unit, which is the empty list, or a list of A, or a pair, sorry, of a head and another list of A, because I cannot recursively refer to this type in a type alias. But still, it should work. And there might be some, forget about this, but there might be some tricks to express that. So that's it. All my types, all my data types, can be summed up with only three elements. It works, of course, for case classes and seal threads, right? Because a case class is just a product. So for example, if I have a product here with only one field, I can say it's isomorphic to this field. If I have 2 fields, or 3, it's isomorphic to this nested product, and so on and so forth. And of course, the seal trait is isomorphic to the sum, the either. So that's it. All we need to do, all we need to express or to represent any possible ADT is unit, a binary sum, and a binary product. But of course, it wouldn't be very convenient, right? Let's just look back at this byte. So imagine a string, for example, or something, an integer. Writing integer like that would be very, very complicated. So maybe in our library, we will need some convenience representation for primitive types, string, int, boolean, and so on. And of course, we will need something for lists or sequences, and also records and union. Records and union are, a record is just a product, but with every field tagged with a label, a field name. And the same goes for a union. It's the corresponding thing for a sum. Finally, when I have this very complicated but simple bit but big, not complicated but simple but very big representation, and my concrete type, because I won't be defining my domain model in terms of product of bit, and so on, I need to reify the isomorphism, right? So in our imaginary library, say we have this schema for unit, which is the schema for just unit, and this is the constructor for the sum. We say the schema for bit is unit, sum, unit. And then, if I want the schema for a Boolean, which will be my concrete type, I just have to plug an isomorphism on top of that and say, okay, so I will prove you that, in fact, Boolean is isomorphic to either unit, by providing this isomorphism, and I can choose. So here I've chosen that left would be true and right would be false, but I could, of course, have chosen the other way around. And that's it. It's just two functions. One to go from Boolean to from either unit to Boolean, and the other one from Boolean to either unit. And that's it. Now I wrap my bit schema defined here with the isomorphism, and I get a schema for Boolean. Cool. Well, in the library I'm talking about, because it's not imaginary, it exists, it will exist. It's under development. It's a little bit more complicated. So I hope you're still awake and full of energy, because it's becoming a little bit more difficult. So we define a schema using a technique called recursion schemes. Can you show me who's at least have heard about recursion schemes? Oh, cool. That's a very, very good audience. So recursion scheme, for those who have never heard about it, it's a way to abstract over recursion by decoupling the way you traverse a structure, a recursive structure, from what you want to do with each of its components. Basically, the recursion scheme library will give you the traversals, and you, as a user, you will just define what you want to do with every node of your tree, for example. So there are two libraries for that in the Scala ecosystem: Matryoshka, based on SchemaZ, and Drosty, based on cats. But unfortunately, we cannot use any of those because we are working one kind higher. Let me explain. Our schema, so before I dive into the higher kind of thing, in recursion schemes, when you use recursion schemes, you have to slightly modify your recursive structure to use that. And you have to make it a functor. That is, for example, if I have a tree defined as a sealed trait tree and a case class node that contains two trees, that cannot be used directly like that in a recursion scheme. I have to replace the recursive reference to tree by a type parameter. And my tree becomes a functor. It's tree of A. And in the node, I have two A's instead of two trees. In higher order recursion schemes, I do that, but with a functor instead of just a type. So that's it. That's my pattern functor, the base of my schema. It takes two type parameters, this recursive slot, and A is the type that is represented by this schema. So what I say here, I didn't write the whole ADT, but the most important nodes of it. So a sum, it's a binary sum that contains something that represents an A and something that represents a B. And in turns, it becomes the schema for A or B. This is either, but from SchemaZ it's shorter, so it's better for the slides. Same with the product. A product takes a schema of A, a schema of B, and is a schema of the pair AB. And we have to do that because when we collapse the tree, for example, the schema, that becomes something that isn't a schema, but the result you want to build. But don't worry about it. What's important here is the A and the B. And that's why we need to go one kind higher, because we need to know that the left represents an A and the right represents a B. And otherwise it's almost exactly the same as typical recursion scheme like you have in Matryoshka or Drosty, except that the functions you have are replaced by natural transformations. But that's just, you get used to it. But once you get used to it, you feel very smart. But it's really not a big deal. Okay, so now what? So far what we have a way to abstract over the structure of data, or to represent the structure of data. That's now our schema ADT. This representation is accessible at runtime, and it's not tied to the compile time. Lifecycle extends just the compile time. we still have to define a way to derive operations or type classes from this verification. So what do we call an operation? I could have said type class, but strictly speaking, a type class is supposed to have lows, and typically your JSON encoder doesn't have lows. So I prefer to talk about operations. So an operation on an A is something that resembles a function that takes an A, or returns an A, or both. So from now on, I will just say an f of A. So this operation can be a show of A, it can be a JSON encoder, an EQ, whatever. And so deriving an operation from a schema is the act of coming up with a polymorphic function that for any A will go from schema of A to f of A, f being the operation I want to derive from a schema. And that's exactly what we call a natural transformation from schema to f. So deriving an operation just means building this kind of natural transformation from schema to f. And it's not really the core of the talk, so I will gloss over it very, very quickly, but this is where we use recursion scheme for real, actually. We fold a tree, we fold a schema onto an f. So we provide a function that folds any schema into the corresponding f. So if you give me a schema for, I don't know, a blockchain, I will give you a f of blockchain, for example, parser or whatever. And how does it work? It's pretty simple. The recursion scheme library goes to the bottom of the tree. So at the bottom of the schema, you have your primitive types, int, string, boolean, whatever. It transforms these small leaves, the schema of an int, the schema of a string, into an f of int or f of string. And then it climbs the tree back up. And when it encounters, for example, a prod node, it will take the two fa, fb and combine them together to get an f of the pair ab. And so on and so forth. And at the end, you get an f for your concrete type. So, and this operation is called a catamorphism in recursion schemes, but that's really not that important. So, now we have a schema. We have a way to define derivation from this schema, so to have our JSON encoder and decoder for free, for example. But we will still have to solve the evolution problem. And that's where it becomes very complicated. So let's recap what's the problem. We don't want to carry along all the versions of our ADTs. Each time we change the ADT, we want to change it and that's it. But we still want to guarantee backward and forward compatibility, and if we can, forward compatibility. That way we will be able to evolve our business logic without worrying about compatibility problem when we deploy the application. Or for example, in event sourcing, the problem you have is that your event log is immutable. So if you want to change the structure of your events, you have to be very careful because you will never be able to change the events you've saved in the past. So even if you change the code that represents the events in your code base, you must remain able to read the old events when you restart your application from scratch, right? So backward compatibility is really, really important. And in fact, you can answer backward compatibility with coming up with alternative readers for the data. That is, if from your current version of your event in the code base, you're able to derive a reader that is capable of reading the old representation of the event, you're good to go. So how do we do that? The naive strategy is to first, because not all the changes you will do on your ADT guarantee this backward compatibility. So first, you have to define a set of the changes you are allowed to do on your ADTs in order to guarantee the backward compatibility. Then, and that's the difficult trick, you will define a schema of the old representation, but expressed in terms of the current one. So it goes backward in some way. Then you will use this alternative schema to derive a reader, as you would do in any with any schema, and you're good. So first, let's look at the operation, the changes you're allowed to do on your ADTs. So it's basically just yet another ADT. I've written a few different migration steps here, but for example, you're allowed, and guarantee backward compatibility, you're allowed to add a field to a record as long as you provide the default value, right? Because the old version doesn't have the field, so you have to inject the default value in order to read all messages into your new class that has this new field. For example, adding a field without a default value is not allowed because you'll break backward compatibility for sure. You can rename fields, provided that the new name is not already used in the record, and so on and so forth. That's the simple part. Then, what you need to do is to define representation of the old messages in terms of the current one. So, for example, you'd say, the current version is version 2. I define the schema for the version 2 like I would do for any schema, so I can writing that end. Maybe later we'll be able to derive that at compile time. That's okay. But so I have my current version. Then I say, and that's where you have to focus, okay, to go from version 1 to version 2, what I did is adding the field age. Right, so it's backward. I start from now and I express the past in terms of now, and what I did in the past to get into the current situation. And of course, you can do that for every version. So in the end, you have like a changelog, but in reverse. Is that clear? Yeah? Cool. So for example, let's imagine that the library doesn't provide any automatic way to do that. Let's do it by hand. I have a class person with 3 fields, age, username, and email. That's the current version, the version 2. And I want to say, or I want to come up with a schema that will be able to read the version 1 of person on the wire, in JSON, for example, and give me or build an instance of the class person with all the fields of the version 2. And what I know is that in version 2, I added this age field, and the default value is 0. So what I can say is the version 1, it's like the version 2, but, so it's an isomorphism on top of the version 2. But what I did is, before, the representation of the version 1, before I added the field, was just a pair of strings. The 2 fields, username and email. So what I need is to provide an isomorphism. It's not an isomorphism, but a pair of functions that, sorry. I didn't realize you would be there. Because Julien has written a library about isomorphism and ticks and so on, so he's grinning right now. Anyway, so I built something that goes from my old representation, the pair string, into my new current version of person. And what I say, it's very simple. When I get the pair string, I inject the default value. And when I get the current person, I just obtain the pair string by dropping the field, the age field. And it's not an isomorphism because it's not idempotent. If you run it multiple times, you don't end up with the same, so it's not isomorphic. Anyway, actually in the current version, I renamed that. It's not isomorphic. And I dropped the model call dependency. And so from this schema I just written by hand, I just derive a reader, and voila, I have a reader from that is able to read the old messages and build me my ADT instances at the current state. So cool, solve the problem. Yeah.
Generally, how do you figure it out which parser do you need to use, which version of the parser do you need to use when you receive it?
That's a good question. This is not supported by this is not taken. So the question is, how do you figure out when you receive a message? How do you figure out which version or which reader you should use? And that's the user's responsibility. You can use metadata, headers, whatever. We provide a way to do that, but you have to choose. So that's it, problem solved. Okay, so actually not, because I've written this alternative schemas by hand, but I want to build a library that will do that for you, right? And it's a very difficult problem. Like, I worked 6 months on it, maybe more, and I've found a solution that looked like it will work, and it's pretty complicated. The 4 upcoming slides are pretty hard, so bear with me. The problem is that using recursion schemes, and that's why people use recursion scheme, I lose the structure of the schema from the structure of the schema is not reflected in types. But if I want to be able to verify at compile time that some migration defined by the user makes sense, for example, if you tell me that you've added the field age to a class that doesn't have the field age, the compiler should raise an error. But because we don't have the structure of the schema at the type level, the compiler doesn't have enough information to verify that the migration you want to apply actually applies to this type. So the solution we found was to add a phantom type to the schema that will, in fact, reflect the structure of the schema. And that's where it becomes messy in the code, but anyway. So we added this representation type parameter. It's a phantom type. And basically, it mirrors the structure of the schema below. And so a migration becomes a function from schema of a representation, a structure of the schema representing this type, to another schema representing the same type, but with another representation. For example, I've dropped a field, I've added a field, and so on and so forth. And we use basically just a tag. You would find this pattern, it's Kasas, it's shapeless, whatever. It's really, really simple. So the idea is at the moment we construct a schema, we tag it with the structure it has below the surface, so that the compiler has enough information to verify that the migration apply. But next, you end up in the problem number 2, is that, in fact, our migration are not simple functions, they are dependent functions. That is, here, in this signature, that is not correct, the type R2 depends on the type R1 and the migration you want to apply. And in the general case, no, it's not scalar, it's scalar C. It fails to infer the R2 type. You cannot basically go define or ask scalar C to verify migrations at arbitrarily deeply nested path in your schema. It ends up, the compiler ends up saying that one is not equal to 1. And I almost, when I talked about it on, not me, but my co-author thought about it on Gitter, it almost got Miles Sabin and Rob Norris write swear words looking at our stack traces. It's a win. So the solution was to just give up on generality. It doesn't work at arbitrarily nested migrations, but it works on the first level. So what we did is we decided to force our users, in order to migrate a schema, to define it at the top level. That means that if you have a record with 3 fields, you can express a migration on that record, modifying the structure of the fields, like adding a field, removing a field, renaming a field. But you cannot define a migration for what's inside the field. If you need to do that, you need to define a variable that will contain the schema of your field, the field value, and build your bigger record by referring to this variable. And then it works. But the problem is, when you do that, basically you're not able to define one big schema if you want to use migration somewhere inside. And so you end up defining many, many functions that call themselves to build your big schema from smaller parts. But then, if you want to migrate, basically what you want to do is to modify this function. And so if you want to define version 1, you would have to rewrite all the calls for all the functions that build the build schema. And practically, in the general case, you would rewrite your whole schema for each version, which is precisely what we want to avoid. We want to automate that. So when we hit that problem, it became very frustrating. Because we felt that we fought a lot for the previous problem, and then we realized, so we solved it by just giving up, and we had working migrations, but then we realized that it will never be usable. But then we found a solution to that problem, and this one is pretty fun. The idea is to build, instead of building directly your big schema, you build what could be called a dependency tree, saying, for example, that this schema needs this schema. So we have called that version, and it's basically a H-list, a list of heterogeneous types, that acts as a stack. At the bottom of this stack, you put the schemas that doesn't depend on anything.
Oh, the newest one would be.
Not the newest, no. So version, you would define multiple versions,
Yeah.
right? But in a version, you put all the schemas of all your model, right? And it's like a stack. At the bottom, you put the simplest type, those that doesn't depend on any other one. And we have a implicit machinery that allows you to add something on the stack, a function on the stack that takes arguments, as long as these arguments are already present below on the stack. And that way, you get a stack with more and more complex functions. You can migrate these functions, because you can modify this function by composition. And in the end, when you really need the schemas, there is another implicit machinery that will apply this function in the right order, giving you all the concrete schemas. You have a question?
So does that mean that you can go from V0 to V3, for example, directly?
For?
From V0 to V3 directly?
Oh, no.
You'd have to apply
This,
V1 and V2.
so you would have one version for one version object for V0, one for V1, one for V2, one for V3. But this version, inside it, you define, for example, you say you have a address type and a person type, and the person type has a address field. Okay? So in the stack, you would put address at the bottom and person on top of it. And person would be, in fact, represented as a function that takes the schema for address and produce the schema for person, and so on. There will be an example. But that works in the end. So let's look at the example. It's almost the current version of the API. Maybe it had changed. So this is a version. This is the current one. Oh, and the important thing is that for defining the previous version, you only specify what has changed. You don't rewrite all the schemas. So we have the current version, and we add schemas to it. So it's a stack, but the bottom is on the top, and the top is on the bottom. So this is the schema for user. It has two fields, a name and active. Name is a string, and active is a Boolean. And we have an isomorphism to say, to go from the pair string Boolean to user. This is a real isomorphism. And that is our simplest schema. And then we have, for example, I don't know, a person schema that depends on user. So we define it as a function that takes the schema for user and returns the schema for person. And so on. If we need to have a schema that has a field of type person, we can add it, after this one, by putting a function that takes a schema for person and so on. So that's our current version. And then, for migrations, all you have to do is to say, in the current version, to go from 0 to the current version, what I did is I changed the user type by adding a field called name with default value John Doe. And that's it. And now, with only that code written in my code base, I can get the person v0. I didn't say anything about person v0, but since person has a field of type user, this migration should be propagated to person. That was the point. And so that's just it. When I do lookup person, I get what happens is that this is a stack of functions. They will be called in the right order from the bottom to the top, and it will give me the actual person, schema for person at the version 0. So with the user field that doesn't have a name. Does that make sense?
Yeah.
Yeah, cool. And that's it. We've solved the evolution problem. But that's not all there is, because the schema gives us many, many things for free. Practically any type class, or even low-less type classes. So we get random generators, and this is the actual syntax. Well, you need a few imports, but that's the actual syntax. We can get EQs, we can get orderings, we can get show, we can get crazy stuff like form and UIs. Like you have a schema, and you generate a UI from the schema. And you change the ADT, you change the schema, and that's it. I said for free, you still have to write the schema. But everything else is for free. I finish. You can have Avro formats from a schema. You can have SQL queries and migrations. You could translate the migrations you've written in terms of migration in Scala into SQL scripts to migrate your database as well. And you could even go completely crazy and have fully generic data pipelines without any case class, just schemas. You define schemas of your data, and you have many things for free, parsers, transformers, and so on, without defining any case class. And in the next pull request I will make, the schema itself will be serializable, meaning that this could be really, really generic. Like, I write the code once, and then I deploy it with many, many schemas, different schemas. Or even I have one big data pipeline, and I just trigger jobs by feeding it a schema and saying, there is the data, there is the schema, do your job, without any more code. So, as I said, it's still an imaginary library. I've not released anything yet. It's called SchemaZ. Your help is very welcome if you want to help me get into the first release. We have the schema representation, the derivation mechanism. Migrations and evolutions are still under work, but we have the proof of concept, and we just have to write the different migrations, adding fields, removing fields, and so on. And that's it. This project wouldn't exist without John the Ghost, who spawned the ID, and Dominic, who helped me a lot writing the library, and also listening to all my silly IDs. And that's it. I'm Valentin. I'm working as a solutions architect at 47 Degrees. We are hiring too. So if you don't go to The Guardian, come to us. And that's all I have. Thank you.